Welcome back everyone. So, we are studying quantum Hall effect. Today we will talk about, so we studied the quantum Hall effect in a continuum model starting from a parabolic band as we apply magnetic field. So, you have a covariant derivative, the momentum operator changes to momentum operator minus gauge field. And you must have solved it that if you use one of these Landau gauge, we get harmonic oscillator like solution, and that gives us the energy levels being quantized. And that quantizations we showed it, it is connected to the flux quantization that we studied the first lecture of this chapter, which was the Aronoff-Bohm effect. That flux quantization led to charge pumping, the Laughlin charge pumping, and from today we will study the same problem, but in a lattice, quantum Hall effect in a lattice. So, when we say that we are in a lattice, so we will impose the periodic boundary condition, and once we have the periodic boundary condition, we have a torus. So, we change the topological manifold, and what we will also see that the Landau labels we studied, which were the quantized energy labels, and we will separate it. The separation between them was caused by magnetic field or magnetic flux, and once in a lattice we have a band. So, momentum becomes a good quantum number. So, what we will see is that these Landau labels become what we can call it Landau bands, if you like. And once we have a band, then there will be a bandwidth, and then we will restudy the same thing, quantum Hall effect in that. And skipping ahead, what we will see is that each band becomes a Chern band. We will introduce formally the Chern band and Chern number in the next chapter, but from this chapter we will be able to slowly get an idea about how the Landau labels in a lattice becomes a Chern band, okay, and what sort of a quantum how this topological invariant called Chern number is arising starting from the Landau label. And this was shown by, and it is called TKNN number because it was shown by these people Thaulas, Komoto, Nightingale and Denies, and we will show that this is a topological invariant. The Chern number that we talked about, it is called TKNN number also, and we will see that that is very similar to the Chern number. So, these are the two reference, and it was also studied by many people subsequently, showing that how this Chern band also lead to a metallic edge state. We talked about the charge pumping giving us Landau levels at the edge will have a metallic energy level, and we will see that they will have a metallic bands, okay, and that is what is causing the edge current. And more reference will be and also one of the reference I talked about earlier, so this is by C and also Hofstadter okay, I will show you in the next chapter, next page. I will be able to set up the problem and schematically show the result, but to the full solution of this require numerics. So, it will be good idea to write some small Python code to simulate them and get the result. Okay. And in case you do not know and you do not have the facility to run a code, you can run now on cloud, on Google Cloud, called okay. You can write small codes to run those things. And finally, where he used the model that TKNN did, where they did it in a lattice, and he showed it that if you eliminate the periodic boundary condition, then you will have a finite lattice, and at that finite lattice the same model will give you metallic edge state. So, this also you can simulate it. And what I need you to brush off the tight binding model and second quantization. All right. So, quick primer about how do we do the tight binding model. So, we will study a lattice, and let us take a simpler lattice, and you can generalize to more complicated lattice, and the simpler lattice could be in 2-dimensional square lattice. Okay. Atoms are sitting at the corner, and we will use 1 electron per atom for simplicity of the calculation. So, what we do is that at any site, let me start with 1 dimension. So, at every site we will have, we will index it by I, and we will have a local state I, which in second quantizations we write it as, and we will not consider spin here, an electron is created at that site by this creation operator. Okay. So, if that is the case, then we can write the Hamiltonian with I plus 1, I minus 1 site with the hopping amplitude t, and it's a common practice to consider minus t, but it doesn't make much of a difference if you take t to be plus here also an overall plus sign. Okay. So, we have some T hopping going from site I. So, destroying at site I and going to site I plus 1 and destroying at site I going to site I minus 1. So, generally these two are Hermitian conjugate. And now every electron has some chemical potential at each site. So, mu being the chemical potential. Okay. And now in the second quantization, this can then be written as so particle is destroyed here and created at I plus 1, okay. And we do not write the vacuum state anymore, and we will use the Hermitian conjugate for the other one, this one, from going to I to I minus 1 and minus mu I C I dagger C I. Okay. And we assume that everything we do, so this is our unit cell. Right now I chose 1 dimensions. So, here to here it is a length of A, and everything is periodic after that, and generally we also take a total length 1 to Lx, and everything after that is also we assume to be periodic. So, that makes it a circle, okay. And later on we will add the second dimension. And because it is a periodic and it is a translational invariant system, so the way we diagonalize this Hamiltonian is through Fourier transformation, and we use Bloch's theorem, and this is the number of electron along this x direction. Okay. So, there are two I, and this is a common notation we will keep on using. So, this I is of course the imaginary I, iota, and this is the length or the distance of the ith particle from some coordinate, from some center of the coordinate, right, and this is the notations we will use. Kx is the wave vector and kx are periodic So, if you do that, then this is the band structure one gets, where so this thing along this direction gives you e to the power I k x a, along this direction it gives me e to the power minus I k x a, and as you sum them here, because it has exactly the same hopping, e to the power I kx a and e to the power I kx minus a, if you sum them you will get twice cosine k a and kx a, and one does not always write this. It is often implicit that there is always a multiplication of a, and these are defined with respect to a. So, kx is rather would be defined like 2 pi by okay, so n will be integer. Minus mu, the chemical potential, and if you plot it you will get a, generally one plots it like this, minus 2 pi by a, or generally 0 to 2 pi is the 2 pi by is the, so we often plot it from pi by to a. One can also plot it from 0 to 2 pi by a. Okay. All right. And these are the Fermi level. Because we are subtracted from the chemical potential, so the Fermi levels will be at 0 energy. All these states are filled. These states are empty. Okay, so these are the things for magnetic field equal to 0. Would you get a band structure? Before we add the magnetic field, let me just generalize this thing to 2 dimension is what we want to do, and what we want to do is that there is now a magnetic field perpendicular, and this is a 2 dimension. So, we will have Lx this side and we will have some length Ly with B being the distance between the unit cell, and we will also include an index I, j, 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 and whereas this side will be I, j plus 1, I minus 1, j minus j plus 1, I plus 1, j, and so on, I minus 1, j minus 1, I, j minus 1, I plus 1, j. And we will also assume for simplicity that it is a square lattice, which means the hopping along this direction is also same. Okay. So, then one can just introduce these indices I plus I and j, and I and j, comma j, comma j, and then again the hopping from j to j plus 1, I will do it again, but let me just show you that it is just adding one more indices. And so on, and you can do the same thing. And what do we get? We will also get minus 2t cosine QYB. Okay. So, we will have plus QY, we will use Ij, Yij, okay, and we will have and you can generalize this to 2D. So, you will have a parabolic band. Okay. So, this is just going to 2D. In fact, I have not yet put B, but now I will going to put B magnetic field. So, now if I put a magnetic field, if I put a magnetic field which is passing through this, an electron going from this side to this side, it will be parallelly transported, right. So, every wave function will now have a e to the power I, a phase. So, I just have to parallelly transport it, right, e to the power minus I E by H cross some initial point going to I and J A dot dr. Right. Now, there is the trick called chiral substitution, and this is indeed the chiral substitution. We have just put it a parallel transport, and we have talked about what is parallel transport and so on. So, we also have talked about getting this phase in a continuum model, right. And now, you see that here, so everybody will then have a parallel transport, and both of them, if you start from some initial point, then you go to I plus 1, and then this one also will have some initial point to, sorry, here it is I and j from some initial point which we can choose any reference point or base point, and then here I plus 1 j to here. So, eventually it is the chiral phase from I j to I plus 1 j that will survive. The initial point will cancel from both, because this is brass state and this is a kth state. So, there is a complex conjugation of this phase which will cancel the initial point. So, eventually what will have the so, eventually the phase that will survive is I j point to I plus 1 j a cross dr, right. Okay. Let me rewrite this, it is probably not visible. So, we had t here and now we have minus I e by h cut I j I plus 1 j alright. So, now this one is associated with this term, coming from this term, and what one does is that one can put it here or one can also modify the t and say t has gone to e to the power minus I by h cross e, the spiral phase, and both are equivalent. Okay. And that is what we will do. So, what we will do is t for hopping from I to I plus 1 will j to I plus 1 j is equal to the original t e to the power minus I okay. Now, this is a choice and I want to be consistent with my notes, and you will see that it does not really matter, is that it is plus and here I think it will be minus, and I think from here to here then it will just the plus sign will remain. Okay. And this way it will again be the same thing, right. But this is equal to so now what we will do is that as we do for Landau label problem, we will make a choice of the gauge field, and B is equal to B z along z direction, and there is no z component, the vector potential and let me see which one we will choose. So, we are going to choose this. Okay, and we will use this. So, this is the Landau gauge. Choose. So, now you see some interesting thing. So, from here to here it is only along x direction. This is a only line integral. So, the y direction dy. So, this one we can split it into ax dx plus ay dy, and needless to say in this case dy is 0 and in our choice Ax is 0. So, there is no parallel substitution in this choice of gauge along the x direction for hopping from here to there, whereas this guy then will be Ay dy going from I j to okay, it is the same. Okay. Minus b x I, so x means x I. I j plus 1 so it depends on the parallel substitution is along the y direction j to jy along this direction, but it depends on at what x value we were substituting it, right. So, as the electron hops from here to there, it acquires this phase, but whether it is hopping from here to here or here to here, there is an overall x a x I that will matter, right. So, y along y direction the distance is b, and I put a tilde saying that it's from some reference I need some a tilde. Okay. So, this guy is nothing but flux. And so, as it is true for any magnetic field, and now even for this choice also, once we have this vector potential which are dependent on the position coordinate, and since position and momentum do not commute with each other, so momentum is no longer a good quantum number. So, going to Fourier space and diagonalizing it will not work, because these k values are no longer the good quantum number. Except in this choice, however, there is a x that is there, but there is no y. So, that means along y direction we still have a good quantum number. So, that means this is still remains our unit cell, and ky remains a good quantum number. But what about along kx direction? Now, because px and x do not commute, so kx is no longer a good quantum number, and you do not have a periodic boundary condition anymore, and that is pretty obvious. In fact, from here maybe I can go back to the x y. saying that the phase actually depends on x. Right. So, when you do a Fourier transformation, you will see that you will have x and p both in the exponential. So, they do not commute. So, you do not have a periodic boundary condition, and this is where the trick of Thouless TKNN came. What they assume is that this is still a flux, and when it is a flux, there will be for a given value of B, capital B, the magnetic field, and small b is fixed. For a given value of magnetic field, I can always find and make x I a variable to the extent that this flux becomes quantized with respect to we choose x I equal to we call A tilde such that B, A tilde and small b is equal to some integer times flux quanta. We can always choose that, right, that is a number. So, what we are doing is let me put one more. We keep the y axis same. So, now this becomes our unit cell or rather supercell. Why? Because now if I have and which involves a flux value of phi equal to q phi 0, and why it becomes an unit cell? Because you see e to the power now minus I e by h cross phi. So, then e by h cross we write as divided by flux quanta times 2 pi, as flux quanta is h by e. Q and q being integer. So, by this time the electron hops from here to a distance of a tilde, the total phase it acquires is integer multiple of 2 pi, which is 1. So, the parallel transport so it sort of forms a loop, this right, the wave functions come back to itself and it sort of forms a loop that we talked about in the first chapter. And in this direction also it is the b direction. So, yeah, or we can so it is actually form a loop, and along this direction also it is a loop because 0 to b it is the the phase is anyway 2 pi because of the periodic boundary condition along p direction. So, it actually forms a torus, and this is called magnetic unit cell. So, you will have torus. Okay. So, this is of length. So, right, of length. So, magnetic unit cell has a length of a tilde b. Now, the thing is that can I choose a tilde to be equal to an integer times a, because b is changing continuously and a will then also change continuously. Can I, and it can be any distance between the two atomic positions, right? Atom has not moved, it is the definition of the unit cell. So, see, the thing is that even if the a tilde is here, I can always continuously deform into bring it here, because here going there is no atom, it does not really make any difference. I can always choose the unit cell to bring it here. So, I can make the loop slightly smaller for our convenience and nothing really changes, and that gives us the freedom that p can be integer. So, which means the magnetic flux we are writing equal to b a b p, which is equal to the flux per unit cell times p, and flux per unit cell is q. Actually, yes, I think this is equal to q flux quanta. So, flux per unit cell, which we will just call phi, then is equal to q by p phi 0. Let me call it flux, and then the phase, or let us just define phi. Okay, we will use it in the next class to be 2 pi times p by q, and this is another equation. Okay. So, now we will draw the band structure and tight binding model in this magnetic unit cell, which includes a flux integer, which is integer multiple of this, and in which we have done is that we have extended the unit cell to a supercell or magnetic cell with this much length. A tilde is equal to p times. So, we have just expanded the unit cell by p times. All right. So, we will stop for this class here, and we will come back for the tight binding model in this magnetic unit cell. Thank you very much for your attention.